Hello. So we're going to be doing lecture 9 today, going over ordered and sorted containers and sets. We're going to look at how to write a function properly that deals only with iterators and knows nothing else. We're going to look at how to do a very interesting algorithm on how to keep track of connected sets. So let's get into this. So when we talk about containers, we're talking about objects that store a variable number of other objects. So when we say container, we don't mean something like a structure that has, 3 integers in it. We're talking about things like vector and dec, etc., that can have a variable number of things in it and generally can have things added to it dynamically. Array, the C++ standard : array that Professor Darden mentioned last week is a weird one. It's part of the STL. It is a container, but it's a fixed size when it's created. You can't grow it afterwards. So that's kind of an odd one there. We want to have our container types allow for some sort of control and possibly protection of data. Things like, say, a stack prevents us from modifying anything but the top of the stack. A priority queue lets us add anything we want, and it might become the top, it might not. It depends on the priority that we specify when we create the priority queue. When we have a container, we might be able to, say, copy the entire container. We might be able to copy certain elements, like a range out of a container. We might be able to edit elements of a container. We might be able to sort a container, move objects to another container, etc. It depends upon the things that the container allows us to do. For examples of this, obviously things we used in Project 1, vector and dec. We're using vector again in Project 2. The priority queues that we're learning now, the other things like the stack and that we mentioned in queue, map, which I believe 280 mentions now. We're going to talk about more in detail after the midterm. When we get to Project 3 stuff, we're going to talk about maps and unordered maps, etc. So, and actually, sorry, one other thing on here, the nested containers is actually really important. When we look at putting containers inside of containers, that's what gives us real power to create complex data structures. So for example, in Project 2, you might have a structure for a stock. You might have a class for the stock market. So I might have a class for the stock market that contains a vector of stocks. That vector of stocks contains stock objects, which contain priority queues, which contain order objects. So we might have 3 levels of containers and 2 levels of structures to create that complex data structure to represent Project 2. So types of containers. So every container has some way to get things in and to get things out. Again, array is an oddity here. Array is a fixed size up front. But when we talk about container, generally we expect things to be able to be added and removed as time goes by. And the function name may change. It may be push and pop. It might be push back and pop back. It might be insert. And the remove function might be called erase or pop. So there's all kinds of different names. A searchable container here, when we say searchable, we mean something very specific, that it has some sort of built-in member function to find things inside of it. And it might be called find, it might be something else. So in this respect, a vector wouldn't really be a searchable container. A vector is a container. We can iterate over it. We can write our own sort of find, but vector doesn't provide a find member function. Containers that do provide a find member function, examples would be map and unordered map. Like I said, we'll talk about those after the midterm. Now, another way we might classify a container is how does it keep the underlying data? Is it sequential or not? Does it keep the data sequentially like a vector does, like one after another, where we can iterate from one to the next? Does it provide random access, where we can skip to an item based upon a number? Is a container ordered? So does the container and the operations that it provides maintain the current order? And that's with respect to anything not being added or inserted. So for example, in a queue, when I add something at the back, other than the thing I added, nothing else changes its relative order to each other. Even a vector, by the functions that it provides, other than modifying something directly with square brackets, the member functions keep a vector sequential. When I insert, I give the insert member function an iterator, and I say, put a value here. Or if you look at what insert has, it has multiple versions. There's a version of insert that accepts an iterator and a value. There's a version of insert that accepts an iterator and two iterators and says, I would like to insert at this point everything in this range, inclusive, exclusive. But when we do those things, the other elements that were already there don't change their relative position. The things that were before what we inserted stay before it. The things that were after it move over to make room, but they all maintain their order relative to each other. The only thing that changes is their order relative to the brand new elements that just got added. So that's what ordered means, is that when you add or remove something, anyone not involved in the add or remove maintains their own relative positions. And then a sorted container, it says a sequential container with a predefined order. So not only does adding something keep everything not added in the same relative order, it also, the new element must be in sorted order. So examples of these last two, we said books on a shelf. The second one says students sorted by ID. A better example of a sorted container would be, well, project 2. Sorted, probably has disappeared, sorted PQ is a sorted container. One that is not ordered would be unordered PQ that we provided for you. It really is unordered, and it's unordered because of how we pop things. If you look at unordered PQ, when we say pop, which means the highest priority element, we don't find it and then move everything over by one. We find it, replace it with what's at the back, and then pop back. So the element that used to be at the back that wasn't the one being popped changes its relative order to all of the elements between where it was and where it ended up. So it really is well named as an unordered container. What's another example of an unordered container? From project 2 would be the binary PQ. Because when we have the binary PQ, let's do a quick example. Let's say low value is high priority. So I've got in my binary heap, I've got 3, 1, 2. Now in our array representation underneath, or really our vector representation, that would be 3, 1, 2. The root element is at index 0, and the other elements are at that. So if I say pop, and oh whoops, see this is highest priority. This is highest values, highest priority. That's okay, it works fine. Okay, so if I say pop the element with the highest priority, well, we replace the highest priority element with the last element. So 3 gets replaced with 2, and we pop back, which we put a 2 here, and we get rid of that element. Well, now look at what happened. 1 used to come before 2. Neither 1 nor 2 got popped, but they changed their relative order. So the binary PQ is an unordered container because of how pop occurs. And we could show similar instances of push, where pushing something causes a reordering of the elements in the array because it has to be fix-upped. Okay, so this is like I said, what I was talking about in the previous slide is what does it mean to be ordered? So we already went through that. And when we implement a container, behind the scenes, we might choose to implement it as a linked list inside of our new container type. We might implement it as an array or a vector or something like that inside of our new container type. And excuse me, as we saw from the slides at the end of the previous lecture, or was it 2 lectures ago? When Professor Darden went over the graphs. Yeah, that was 2 lectures ago when Professor Darden went over the graphs of the timing of the different things in the STL. We showed how linked list wins if we're inserting at the front. It wins over vector. But dec is pretty good overall. Vector beats it in some places. And someone asked in office hours yesterday, they said that they had tried using, for their priority queues, they tried changing the default. Because when you make a priority queue, you either say priority queue of X and you're done because it's already got a less than operator for type X. Like I can say priority queue of int, and I get a priority queue of integers where highest value is highest priority. But if I want to override the functor, I have to say priority queue of type X, comma, underlying container, which is usually vector containing X, comma, functor type. Well, what someone said was that they tried replacing vector of X with dec of X and wanted to see what would happen with their project too. And one of the tests they went way over on memory, and they, so we talked about why that might be. But the real takeaway is that when the STL developers decided that the default for a priority queue would be vector, they had a reason. They did a bunch of analyses, and they decided that that was the most efficient container for most people's uses of a priority queue. And so the student said he had a few test cases that got a little bit faster, but he had one test case that went way over on memory, and it was just how that test uses the priority queue just happened to go way over on memory, like double the memory requirements, which is, I was a little bit surprised that dec would go over by that much. But it all has to do with how it allocates memory and how containers don't like to give up memory. So for instance, if you have a vector and you push a million things and you pop a million things, the size would be 0, but the capacity would be 1,000,000. The memory is still allocated. It doesn't like to give it up once it has it. And so that can affect our memory usage. So like I said, the takeaway is that when you create a priority queue, the underlying container is vector for a reason. When we create a stack or a queue, by default, the underlying container is a dec. And you could do a linked list if you wanted to, but there's reasons not to. So you really have to look at what is the operations you'll be doing, how often do those operations happen. So if I'm going to, I say, well, I'm going to be inserting at the front, I've got to use a linked list. Well, if it turns out that I do insert at the front, but I only do it 0.1% of the time, that it's very, very rare that I insert at the front, then maybe a vector is still fine and wins on the things that it does real often. So we've got to look at those different aspects of what do we do, how often do we do it, and how does that affect our overall speed. So like we said, when would a linked list be preferable over an array? If there's lots of inserts given iterators. So if I insert given an iterator in the middle, then linked list is the winner. Nobody beats linked list. Once you have an iterator to the middle, inserting a new element in the middle is O of 1. And the middle is the absolute worst position for a dec. If you look at dec insert and dec erase, it is O of the distance to the closest end. And vector, it's always the distance to the back is how long an insert or an erase takes. So vector, it's always your distance to the back. Dec, it's your distance to the closest end. And the worst place for a vector is the beginning to insert or erase. The worst place for a dec is the middle. So we've got a bunch of operations that we'd like to do on an ordered container, and we want to know how long they would take. So adding an element, so I say here's a value, just get it into the container. Well, I can do that with O of 1 time. I push back to a linked list or a vector. When I remove an element, given a value, they're both O of n because they both have to find the value. They've got to go through the container, find the value, and it could be the last place possible, like I could start at the beginning and find it at the very last one, or it could be that the value's not in there. Either way, it's going to be O of n time. For a remove given an iterator, it says for an array it'll be O of n. So the reason for that is that even though I've got an iterator, it could be that I've got to move everything else over that comes after it. So I could get lucky. I could be O of 1 if it's at the end, but if it's in the middle, it's O of n. If it's the beginning, it's O of n. So we're looking really here, we're looking at worst case. And I suppose the slide should say that. Asymptotic worst complexities. Now, the linked list says O of n or O of 1. Well, how can the worst be one or the other? Well, it depends on our type of linked list. So if I've got a linked list, so I've got a head pointer for my linked list, which points to a node, which points to a node, points to a node, etc. And I give you an iterator to this node, and I say, get rid of that node. Well, to get rid of that node, I've got to make this one point to this one's next, which doesn't exist. That's a null pointer. So I've got to modify that pointer. But to get there from the beginning of the list, I got to go back to the beginning, go next, 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 until I get to the one that points to the one that I want to delete. So that's when it would be O of n, would be if it's a singly linked list, and it's at the end. Now, singly linked list in the middle, I can cheat a little bit. So if instead of saying, I want to get rid of that one, if I said, I want to get rid of this one. Well, what I could do is I could say, well, this one has, this is like 2, 4, 9, 7. I could say, okay, well, you want to get rid of 4. Okay, I'm going to overwrite that 4 with a 9. I'm going to make a temporary pointer to this one. I'm going to make that one point to that one, and then I'll delete that node. There, I got rid of 4. So I didn't get rid of the node that used to contain 4, but I did get rid of the 4. So depending on what you meant, I might have done what you meant. But I can only do that if it's not the last one. And the worst case, we get to pick who's the worst. The worst would be the last one. So in a singly linked list, it could be O of n. In a doubly linked list, though, we can always get rid of, I'm just going to do a bunch of erasing here. In a doubly linked list, we can always do exactly what they wanted and get rid of the node containing that value by saying, hey, I've got previous pointers also. So if someone says, get rid of this one, I can say, okay, well, that one, then I go previous, I say my previous next, if it exists, if I'm not the head, my previous next is equal to my next. And if I have a next, my next previous equals my previous. And now I can delete that node, and I really did delete the node you said to delete. I didn't just shuffle values around. So if it's a doubly linked list, we can always do it in O of 1 time. If it's a singly linked list, it might be O of n time. Okay, finding a value, O of n, O of n. We don't know where it is. We got to go find it. If it says I got to dereference, so if I give you an iterator and I say dereference that iterator, show me what it's pointing to, that's O of 1 in either case. It's basically the iterator is just like a pointer. If I say square brackets operator, I give you an index, and I say find me this thing given an index. A vector is O of 1, linked list is O of n because there is no square brackets operator. To get to element k, I've got to go follow the head pointer. Okay, that's 0. Next is 1, next is 2, next is 3, and that's all the way up to O of k, and k could be as big as n. I could ask you for the last element. All right, what about insert after or before given an iterator? Okay, so for insert after or before, let's just look at both of them with an array. With an array, inserting after or before is O of n, because whether I insert something before or after this current thing that I'm pointing to, everything else, or everything else plus 1, has to move over to make room for that new element. With the linked list, insert after is O of 1 because if I've got my linked list, erase a little bit here. So if I've got an iterator and I say insert after this one, well, that's okay. I can just say, hey, let's add a new node. New node points to that one. And if it's doubly linked, it doesn't matter. That one points to this one points to this one, I point to that one. There we go. I've inserted a new element. So insert after can be done in O of 1 time. Insert before, it says O of n or O of 1, depends on whether it's doubly linked or singly linked. Or I should say it's singly linked or doubly linked. Singly linked would be O of n, doubly linked would be O of 1. All right, so that's ordered containers. What about sorted containers? Well, if we do sorted containers, let's jump to the easy ones. The insert after and insert before are gone. Not allowed to have it happen because it must be sorted. You can't say insert Q before B because that wouldn't be sorted. So those are just disallowed. Okay, going back to the other ones, everything that's changed is marked in, I'm going to say red. I'm going to guess there. I think that's red. I could be wrong. So all of the, they're certainly bold. They're certainly bold, then they're a different color. So the ones that have changed are marked in bold and a different color there. So the remove given an iterator, array is still O of n. Okay, I guess the bold, I don't know, it's hard for me to see. Colors, I hate colors. Okay, anyway, so the ones that I know are the finding had to change, right? With an ordered container, we still had to search from the beginning. But with a sorted container, we can do a binary search with an array. With a linked list, it's still O of n because we can't do a binary search on a linked list. We have no way to get to the middle except to traverse everything up to and including the middle. So the find on a sorted linked list really devolves to a linear search. If we try to do a binary search, we could end up doing more work. Right? I say, skip to the middle. Well, if what I was looking for was the first element, I just passed it up and over 2 elements ago, just by trying to get to the middle. So I could end up doing way too much work if I try to binary search a linked list. And if it is near the end, I'm still going to end up doing at least as much work, right? I'm going to go, I've got to go to the middle. Well, it's greater than this, so I go to the middle of the right half. It's greater than this, so I go to the middle of the right quarter. It's still bigger than this, I go to the middle of the right eighth. It's still going to be O of n if I write the code well. If I write the code badly, it could be worse than O of n. Okay, so those are the, I'm going to double check here because I can't see colors. So those are the, and then the add element, sorry. The add element changes. Because it has to remain sorted, the add element has to keep it in sorted order. So in the ordered container, we could just say, hey, in the array or the linked list, just add it at the end. But now, when we want to add an element in a sorted array, we could find where it should be with a log n search, but we still have to move everybody over to make room for it. That could be O of n. In the linked list, it takes us O of n time just to find out where it should be, because we have to do a linear search to find where it should be. Okay, I know Professor Darden revised these slides. He just doesn't keep my color blindness in mind when he does that. Okay, I think we got all the ones that changed there. Okay, so we're going to look at binary search. And you might say, oh, binary search, that's so basic. I know everything about binary search. We're going to teach you some new things about binary search. We're going to expand upon it. So, simple review first of binary search. If I'm looking for 21, I look in the middle. I made it easy here by making a nice odd number, so there's always a middle. If there was an even number, well, then it wouldn't be exactly the middle. It'd be either left of middle or right of middle, depending on how we do the math. But it's approximately the middle. So we jump to the middle. We don't find the 21 we were looking for, but it's greater than what we wanted, so we look to the right. So we look in the middle of that region. Oh, that region doesn't exactly have a middle. So like I said, we're a little bit left of center here, but that's still dividing it almost in half, as close as we can get. So we look for 21 there. So we look for 21 there. That's not what we're looking for. That's greater than what we're looking for, so we look left. All right, we look in left, we look in the middle of that region, and we find what we're looking for. So that's a basic binary search. And the asymptotic complexity, we hope, would be log n. The requirement, though, is that things have to be sorted for this to work. Not only sorted, they have to be sorted in the order that we know that we're searching. Like if we had them sorted in descending order, I would have to write my binary search just a little bit differently to change whether to look right or left, depending on whether it's less or greater. That sense would change, but the rest of the algorithm would stay the same. But we have to be sorted on the same thing that we're searching for. So if I had a bunch of students sorted by name, and then I want to find someone by address, that doesn't help. All right, so here's some binary search code. It says, I give you an array of doubles, a value, a double value to search for, a left and a right, and the left and right here, what we're going to try to do from now on, and I know we didn't do this up until now, we should go back and revise slides before this at some point. We want to have left and right be in this sense. We want left to be inclusive and right to be exclusive because that's consistent with how the STL does things. And it also makes the code for this a little bit easier to write because we're gonna modify this and do something cooler. So we've got a loop here that says while right is greater than left, which is basically saying while there's a region left to search in or remaining. Let's stop using the word left. Okay, while there's a region remaining in which we can search. Because if right and left were the same thing, let me draw it your way. If right and left were the same thing, remember, right is exclusive. So we're saying this one is included, but it's not. We've run out of places to look. So if right ever reaches left, we've run out of places to look. So these are indices. They could just as easily be iterators or pointers, but we wrote it using indices, make you a little more comfortable still. So we've got while right is greater than left. So while there's a region remaining in which to search, figure out the middle index. So the middle index, I take right minus left. I subtract how many elements are in this region, divide by 2, and add that to the left. And I did the math this way for 2 reasons. You could say, well, why don't I just do like right plus left and then divide by 2, right? Because if that was like index 0 and index 10, 0 plus 10 is 10, divide by 2 is 5, and that's the middle index. Well, that works with indices, but it doesn't work with pointers because you're not allowed to add pointers to each other. So this is more generic to do it this way. Also, if the array was really big, left plus right might overflow. Like if I'm near the end of 2 billion elements, 2 billion plus 2 billion is negative a couple hundred million because the integer overflow might occur. So this way the math is also safer. If we had a really big one that was close to the limits of an integer, doing it this way reduces the chances of overflow. Okay, so I find out the midpoint, And then we say, hey, I want to get excited. If I found what I was looking for, that's great. I return mid. So I check for equality first. I say, if this is the value I'm looking for, I'm done. If I didn't return, we could have put an else if here, but we didn't need to because of the return statement ended the whole function. So if it wasn't the thing we were looking for, then I say if this value, if the value I'm looking for is less than what I found here, modify the right to be equal to the middle. Otherwise, modify the left to be the middle plus 1. Okay, so we've got to get this straight. So I've got a container. Let's say like 5 elements here. Okay, so my indices that would be passed in, left would be 0, right would be 5, which is off of the end, but that's inclusive, exclusive. We figure out the middle. Well, right minus left is 5. 5 over 2 is 2. 0 plus 2 is 2. So mid would be right here. So let's say the values in here are 2, 4, 9, 17, and 23. And I say, hey, the value I'm searching for is, let's say I'm searching for 17. So if that's what I'm looking for, I find the middle and I say, is that the value I'm looking for? No. Is the value I'm looking for less than what I found there? No. So I move left. Remember, it's inclusive, exclusive. So I would move left up to here if I was looking for 17. Now, let's say I was looking for, let's just do it in a different color. Let's say I was looking for the value 3. If I'm looking for the value 3, I look at the middle, I see 9. Is the value that I'm looking for less than what I found? Yes. So I would move right to be equal to the middle. And it's exclusive. See, it's exclusive because I've already checked the 9. I don't need to look at 9 again. But when I move left, because left is inclusive, I set it to middle plus 1 because I don't want to check 9 again. So we either move past the middle if we're looking in the right half, or we move to the middle if we're looking in the left half because of the inclusive-exclusive sense. Okay, so that's an example of using that. And I think there's a bunch of stuff written over here. Okay, so I just wrote over the top of that. So we'll clear it out. You can go back in the video if you need to. Okay, so, and it says n is the n. So when we talk about n, when we talk about complexity, we're going to say n is the size of the region, which would be the original right minus left. N gets split in half each loop. Remember, either the left moves up to just past the middle, or the right moves down to be the middle. N gets split in half each time. So n is equal to n over 2 each time through the loop. So if n gets split in half each time, then 2 to the k would be equal to n, and we get a complexity of k steps. K is log of n. So we've done the t of n is equal to t of n over 2 plus a constant, right? We've done that one before. We can plug that into the master theorem. Off we go. So we get log n out of that. Now, the real question is, we're almost there yet. First question is, how do we compare elements that are objects? Okay, so let's say we were searching for a particular student. What do we have to change? All right, well, I would have to change this to a student object. So I'd have an array of students. And then would I have value be a student? Would I say, I'm looking for Anne Leon. She has a birth date of this. She has a student number of that. She's got this exact GPA. This is her address. This is her home country. This is zip code, phone number, etc. No, I wouldn't give all that stuff. I would probably be searching. If I knew all that stuff, I would know everything about her. So I probably wouldn't give it a whole student object. I might give it a name. So my value here, instead of being a double, might be a string, or it might be an integer like a student number. The array of students would have to be sorted by whatever I'm searching for. So if I'm searching by name, it's got to be sorted by name. So then the other thing we would have to change is when we say if val equals a sub mid, we would have to change that slightly and say if val equals a sub mid dot get name. And if a is less than mid dot get name. So we would modify that slightly. We don't compare a string to a whole student object. We compare a string to a string within the student object. So a few little changes needed to make it work on a container, or on objects. Sorry. Okay, so the other thing we could do is we could say, hey, when I like to do sorting and stuff like that, I use functors. Couldn't I use functors for searching? Well, let's look at our functor first, and then we'll go back. We'll look at functors in general, and then we're going to go back to modifying the search. Okay, so we've got our struct point here. And say I want to make a functor for points. Well, then I could make a functor to compare by x, where a greater than x, so they're basically this. If I used this functor to sort, I would get descending order by the x coordinate. And I could create another one, compare by y, which would give me ascending order by the y coordinate. So what I do in the functor really determines the underlying ordering when I sort the container. And if I use these in priority queues, so let's say I put points in a priority queue and I used this one, then obviously X would be determining who's at the top of the priority queue. Which X would be at the top? Largest value at the top of the priority queue or smallest value? Well, think about the question. And this is something you got to keep in mind when you do the project 2. Functors for a priority queue always answer the question, is the priority of A less than the priority of B? And what I like to do here to make sure I've got it correct in my head is I make an example and see what happens. So let's say I had 2 points where a dot x was 5 and b dot x was, let's say, 3. Okay, so the question is the priority of A less than the priority of B? So what we actually test is a dot x greater than b dot x? In this example, it is. So this function would return true. When this functor returned true to a priority queue, it would be saying it is true that A has a lower priority. Therefore, the priority queue would put B closer to the top. So this shows that small x has highest priority. And then in the bottom one, because we compare by y, y would determine the priority, and because it's less than instead of greater than, large values have the highest priority. So if your parameters are a and b and you do a comparison, is a something less than b something, then what you're producing is a max heap ordered on that thing, ordered on y here. So the middle one produces a min heap based on x. The bottom one produces a max heap based on y. Now we can also use these things for sorting, but I just wanted to make sure we've got this straight in our minds, what happens in these. And the other thing is that this works out really nice. Let's say we were using the bottom one to produce a sorted PQ. So I'm using the bottom one to produce a sorted PQ, and I've got, like, again, let's do a dot x is 5, b dot x is 3, and someone gives these things to our, or we're the sorted PQ, right? We're the sorted PQ, and I've got these things, and I call this compare. I say, hey, this compare, what's the deal with A and B? Is A a lower priority than B, yes or no? It would say False. A has a higher priority than B. Well, the sort, when we call standard sort, we're not really, in sorted PQ, we're not really calling this compare. We're calling standard sort. Standard sort is calling this compare. So when we do standard sort, remember a few minutes ago we said this bottom one would produce an ascending order by y, which would mean a dot x should be closer to the back of the vector. Oh wait, I'm drawing it my way, your way. So a dot x would be closer to the end of the vector. A would be closer to the end of the vector, which means it would be closer to the back. If these were the only two things in the vector, A would be at the back of the vector, but that's the most convenient place to pop when we have to pop the highest priority. So it's kind of weird. So a less than functor produces an ascending sort. It produces a max heap, but it all works out great for the sorted PQ because the ascending order gives us the highest value at the back end, and the highest value is the highest priority. So I know it seems strange that a less than functor gives you a max heap, but it does. We have to get used to that. We have to live with it, but it works out really nice for our sorted PQ implementation. Okay, so that's how functors work. So what we're going to do is we're going to speed up binary search. Well, we can't make it any better than log n in the worst case. Best case, we could always get lucky and find it at the middle. But we can't speed up the worst case asymptotic complexity. We can't make it faster than log n. But what we can do is we can reduce the constants. And that's our goal here. We're going to reduce the constants. We're going to make binary search faster by making, first of all, it says, hey, speed up idea equals rarely triggers. In fact, equals triggering means it's going to be true. Equals, when I'm looking at the value, equals is going to be true at most once. But the less than and greater than are going to be true approximately log n times. So let's check less than first, else I'll check if it's greater than, else I'm not even going to do a check for equality, else it must be equal. Or we could put, instead of parentheses there, I could just put like a slash in there, else comment, it must be equal. Okay, so that's the simple thing we're going to do, is we're going to just reorder the tests. The other thing, the more radical thing we're going to do is, let's say I moved the equals check outside of the loop. What that means is we're going to find a lower bound on what we're looking for. So what we're really going to find is we're going to find the first item that's greater than or equal to what we're searching for. So we're going to find where it is or where it should be. Then we could say, hey, let's check for the equals after the loop. Even more radical than that is I'm not even going to do the test for equality. I'm going to tell you here's where it is or should be if it was in here. This is the lower bound. It's up to you. If you want to do equality, you do equality. That's your thing. I just find where it is or should be. Okay, so here's the original version. And what it says is almost always 3 comparisons per loop. So we've got one comparison is done on the indices. And usually we don't count those as things because they're not comparing data, but we're going to count them here because we want to see just all the comparisons, period. So comparison 1 is comparing the indices. That's always going to have to happen. Then we do comparison 2, and comparison 2 is seldom true. So we often do, most of the time we do comparison 3. So we almost always do 3 comparisons per loop until we find it. So if we just reorder things, so I do the less than check first. So I always have to do test 1, am I within the bounds? Test 2 is going to check less than, and 50% of the time, this one's going to be true. So like 50% of the time, I'm done. So this one, it says 2 comparisons half the time. So I always do 2 comparisons, And about half the time I have to do a third comparison. So I've gone from 3 comparisons on pretty much every loop to 2.5 comparisons on pretty much every loop. The other thing we did is we eliminated the need to use greater than. Notice we did less than on both of these, and we reversed the thing. So if I want to say, like, if B is greater than A, I could instead change that to be if A is less than B. And the reason we do that is the reason the STL does it. The STL likes to not force you to overload everything, right? If you want to give a data type to, say, sort, it doesn't have to support less than and greater than and equal. It only has to support less than. And that's why a functor overloads less than, is that that's what's most often needed to accomplish everything we want to do. So that's why in here we wrote it in this order, is so that, hey, if we wanted to make this work on iterators and a functor, if I want to make it work with iterators and a functor, then I would need a single functor that only does less than. So that's another side benefit of doing the less than and the opposite less than first and never testing for equality, is that we don't need an equality operator. We just need a less than operator. So there's our first change, is reorder a little bit. Second change is there's no longer a test for equality in this function. So we say, if as long as right's greater than left, so that didn't change, we figured out the midpoint. If A sub mid is less than the value, we move left, else we move right, and that's it. And then when we're done, we return left. Wait a minute, we're going to have to do an example of this one to see what happens. All right, so here's, oops, sorry, I thought there was another slide in there. Okay, so let's do an example. All right, so I've got values, got to be sorted. 2, 4, 9, 17, 23, I think is what I did. Okay, and let's say that the value I'm searching for is, let's search for something that is there, and we'll make an easy change to something that isn't there. So we'll search for 17, and then we'll say, well, what would happen if we were looking for 16? All right, so I'm looking for 17. So I say, figure out the midpoint. Midpoint would be here. And is A sub mid less than the value I'm looking for? Yes, it is. So I move left. Okay, so left gets moved to here. So that used to be mid. So now this is left. This is right, is still off the end. So left used to be over here. It's not there anymore. Right is still off the end. Okay, so then we come back through the loop. While right's greater than left, it is. Figure out the middle would be, the middle of this would be right minus left would be 2. 2 divided by 2 is 1. Left plus 1 is here, so middle would be right there. So that would be the midpoint. And we'd say, is A sub mid less than value? No. So therefore we set right equal to mid. So we move right over to here. So that's right. We go back through the loop. While right is greater than left, it is. I figure out the middle. Middle would be right minus left would be 1. 1 divided by 2 is 0. 0 plus left is left. So now mid is there. And I say, is that one less than the value I'm searching for? No. Therefore, right gets moved to mid. Okay, so right is now here also. So left, middle, right, all the same place. Come back through the loop. Is right greater than left? No, it's the same, so the loop is done. And we return left. Oh, look at that. Left actually refers to what we were looking for. Now, what if the value was 16? Everything would happen exactly the same, and we would return saying that's where 16 is or should be. If 16 was in there, it would be there. And so this function is called lower bound. This is very similar to what the STL lower bound function does. And lower bound, you're going to want to use it in your sorted PQ. See, here's the nice thing about this. When we return, so I say, hey, I'm looking for 16. Think of it in terms of sorted PQ. Someone just did a sorted PQ push of 16. We call the STL's lower bound, and it tells us 16 should be here, and it returns an iterator. Well, hey, we say, hey, data vector dot insert at that iterator this value. Well, the way the insert works is it's basically an insert before. It says, oh, you've got an iterator and you want to insert it right here. That one and everyone after it has to move over one, and I put the new value right there for you. So this works out perfect for the sorted PQ. So your sorted push should really be like 2 or even 1 line of code. You can put this all into one call. You can say data insert. What's my insertion point? Big long call to lower bound, comma value. So sorted push can really be 1 line of code if you use the STL to make it happen. And so what we've done is we've turned our basic binary search into what the STL's lower bound is like. Now, we still want you to use STL lower bound. 2 reasons. 1, it returns an iterator, and that's what data insert expects. And 2, because it uses iterators, it's faster than using indices. And it was written by the STL people, so they probably did some other crazy optimization too with the iterators to make sure it's just the most efficient way possible using iterators. Okay, so in the STL does have a function called binary search. Unfortunately, binary search, I'd like to say binary search is less than useful, because binary search returns a bool. It returns true or false. Is it there? Is it not there? Lower bound returns an iterator. There's another one called upper bound. Upper bound basically tells you the last possible place it could be. So if I had like 2, 3, 5, 5, 6, and I say find me the lower bound of 5, lower bound of 5 is here, upper bound of 5 is there. It's the last possible place 5 could be. And so if you're looking for where are the 5s, you could do a lower bound and an upper bound, get an exclusive, inclusive exclusive iterators to the beginning and the end of the 5s. But hey, there's also an equal range that does both at once. So you really wouldn't do upper bound followed by lower bound. If you're looking for an exact match, we would use equal range, and it gives us a pair of iterators that are all the ones equal. So yeah, so Professor Darden says it's the first place it couldn't be. First place it couldn't be, which is equivalent to the last place it could be, whichever way makes more sense to you. Okay, so that's lower bound and stuff. And so, oh, and there's an example here. That's a slide later than I thought. So lower bound, so if we call lower bound begin and end of 7, what it does is it looks there and it says, hey, that's not 7. I've got to look in the left half. And so that's the region I'm restricted to. All right, well, then it looks in there, it sees 3, and it says, oh, I've got to limit the range I'm looking for. Then I do 5. Okay, that's not the 7, so that restricts the range I'm looking for, and that's where it is. And an example, what if I was searching for 26? I look at the middle, that's not 26, so I can eliminate the beginning. I look at the middle, that's not 26, so I eliminate the beginning. I look at the middle, that's not 26, so I eliminate the end, and that's the lower bound of 26. That's where it would be if it was in there. And then if I'm looking for 21, if I'm doing an upper bound, so I'm doing an upper bound of 21, I look at the middle, that's not 21, so I eliminate the beginning. Look in the middle there, that's not 21, so I eliminate the end. But I have to keep 25 in there. So then I go, okay, let's go to the left half. What about that one? That's 21, so I look to the right of that one, And that's the last place I can look. And I've got a region down to size, basically down to a size of 0 region. If I was doing the upper bound of 4, we look at the middle. That's not 4, so we eliminate the end. Look at the middle, that's not 4, we eliminate the beginning. Look in the middle, that's not 4, so we eliminate the end, and we're left with only one place it could be. Okay, so representing sets. So suppose we wanted to do some operations like union, intersection, etc. And simple things like add an element, is this element in there, is this set empty? We could use some sort of container. So what we'd like to do is we're going to do an example here, and what we're going to do is we're going to make a few restrictions on our sets. So first of all, our sets are going to be sorted ranges. So what we consider to be a set is going to have to be a sorted range. It could be a sorted vector, a sorted linked list, sorted deck, doesn't matter. It's just got to be a sorted container. And one other thing is sorted ranges and no duplicates. So we're not going to allow duplicates. So duplicates can't appear in the input, and then we're going to guarantee that when we produce the output, there's not going to be any duplicates in the output either. So let's look at how this works, and then we'll look at the code for it. All right, so we've got Amy and Amy. All right, we do a union. We copy one of the Amy's to the output, and we move forward in all of the containers. And you notice the iterator over on the right, the green one, I think, the green one in set 3 is pointing to just past the Amy that we wrote. This is going to be important later on. So Beth and Blake, for set union, Beth goes to the output iterator moves forward, and the set 1 iterator moves forward. Brian and Blake goes to the output iterator moves forward, set 2 iterator moves forward. Brian and Bob goes to the output, iterators move forward. Brian and Brian, one Brian goes to the output, all the iterators move forward. Now, when I'm at the end of set 2, what I could say now is, hey, everybody left in set 1, let's just copy you to the output one at a time. So Dan gets copied, Emily gets copied, Frank gets copied, and we're done. And we've produced the union of set 1 and set 2. Now, for that to happen, the iterators into set 3 had to be valid. They had to be able to put things there. We'll talk about how to do that in a few minutes. Now, here's the code. Bit ugly, I know. Let's break this down one piece at a time. So the first is the template line. We've got for iterator. That stands for forward iterator. Remember Professor Darden talked about the different types of iterators. So a forward iterator, so remember, what can we do with the iterators? All iterators we can plus plus. All iterators can be copy constructed, which we did here. We passed iterators by value. All iterators can be dereferenced. Forward iterators can be read from, and they can be read multiple times before you plus plus them. Input iterators, when you dereference and read, you must immediately plus plus before you read again. But forward iterators were allowed to look at that thing multiple times with dereference before we move forward. And that's going to be important in this. Okay, so then we've got forward iterators 1 and 2. Those are the iterators into container 1 and container 2. And the reason there are 2 of them, 2 types, is that, maybe this is a vector, and maybe this is a linked list, and maybe this is a deck. So that's why we've got 3 different types of iterators. 2 different types for the input iterators, because they could be 2 different types of containers. They could be 2 different types of iterators. And then we've got the output iterator type, because the output type could be a different type of container. And then class compare. Compare is this functor that's going to help us do our job, because I don't know what's in these containers. I don't know how to compare them. I've got a functor to help me. Okay. Now, other thing that we can do with forward iterators is we can compare them to other forward iterators of the same type, which is what our while loop does. So our while loop says, well, first one is not equal to last one, and first two is not equal to last two, is basically saying while I'm not off the end of either container, while I am within both set 1 and set 2 containers. So while I'm inside of both containers, I call compare of dereference first 1 and dereference first 2. So that's like in the previous slide when I looked at like Amy and Amy. So I do a comparison, and really the comparison is I'm asking, it says in the comment here, is set element 1 less than set element 2? That's what the compare is doing. It is a less than compare. So if that was true, if it was like Blake and Bob, then I would say, okay, send to the result what's in container 1 and move the iterators forward. Now the syntax here, I believe Professor Darden went over this in a previous lecture. The syntax here is important and the order is important. So what this says is dereferences happen first. So I dereference first, I read from it, I dereference result, I write to it with the equal sign, and then the plus pluses happen. And the plus pluses happen on the iterators, not on the values. If you try to put parentheses around this, it'll go wrong. You've got to do it exactly this way when you use dereference and plus plus at the same time. So this says dereference the value, but plus plus the iterator. Because the plus plus resolves, the post increment resolves from right to left, and only resolves on one thing. It resolves on the iterator. So this says read from first one, write to result, where it points to, and then plus plus first one, plus plus result. Which order the plus plus of first one and result occurs in, I don't care and I don't want to know. They both happen. All right, then it says else, if that wasn't the case. What if we had like, let's say Amy and Blake. If I had Amy and Blake, well, what if I compare first 2 and first 1, dereference? Well, because I only have a less than operator, I have to reverse the operands. Remember when we said when I want to do if B is greater than A, I can say if A is less than B. So that's what we're doing here, is we're reversing the parameters. We're using the same comparator. So if this compare says true, it means the thing in set 2 is less than the thing in set 1. Therefore, the thing in set 2 should go to the result, and set 2 and the result should get incremented. Else, well, if it wasn't A less than B and it wasn't B less than A, it must be equality. And so somebody has to get copied to the output, and everybody has to get incremented. So I chose to copy from first 1 and then increment first 2 in its own separate statement. If I reverse the 2 and the 1 here, it still works just fine. I've just got to do all 3. I've got to copy from 1, and everybody has to get incremented. In line 13, why did I make it a pre-increment? Because pre-increment is slightly faster than post-increment with iterators. In the other lines, it has to be a post-increment because I have to copy what's there before I move to the next element. But with line 13, because it's just happening all by itself, just move first 2 forward, because I'm just moving an iterator forward, I just do a plus plus as a pre-increment. All right, that's the end of the else, and that's the end of the while loop. So that gets, as long as I'm within both containers. Then the last part is basically saying, take care of the remaining elements. While I'm not at the end of first 1, copy from first 1 to the result. While I'm not at the end of first 2, copy from first 2 to the result. And at most, one of those loops is going to run. If I ended up with both of them being on like Zebediah, and I ran off of both at the same time, then neither while loop would run. But they can't both run because the first while loop stopped. The first while loop stopped because at least one of them was off the end. So at most, one of those two while loops can run. Then when this is all done, I return result. And it says return the end of the sorted union of set 1 and set 2. But remember what sense we have. I know from outside, I know where I told you to start putting things, right? I told you start putting things at result. And I know, remember, I gave it to you by value. I gave you a copy of an iterator. So I've already got an iterator, let's not call it result. I've already got an iterator that tells me this is where the output begins. Output B. So I've already got output B. You return to me result, which is just past the end, and that's what the STL likes, is inclusive, exclusive iterators that enclose a region. So it is really important that that thing return an iterator to just past the last element. So that's what that accomplishes. Now, when we do that, we've got to, and I don't remember it in the next slide, okay, we've got to talk about how to call this. Okay, so yeah, Professor didn't put that in there. He edited the slides, and I haven't done this lecture lately. Okay, so how do we call this? There's two ways we could do it. Let's go back to the previous slides. Got some room here. I'm just going to go back to the beginning of this one. Okay, yeah, there's the beginning. Okay, so that's the beginning of this one. So when I go back to the beginning of this one, one thing I could do is I could make set 3. We said, hey, what if set 3 was a deck? I could resize set 3. How big would it have to be? Well, here I've got like 1, 2, 3, 4, 5, 6 elements and 4 elements. If they were all unique, I could have ended up with 10 elements, right? So I could, one thing I could do is I could say like set 3 dot resize to be basically set 1 dot size plus set 2 dot size. Okay, so I could resize it, and then I would say like auto it is equal to my set union, and I would give it set 3 dot begin would be the place to start writing. And it returns an iterator to me. I use auto here because, yeah, I know it's going to be the same type of iterator that set 3 is, but rather than saying like deck angle brackets int colon colon iterator space it, I say auto. Figure out the type of that iterator for me. Now what I have to do is, if it didn't fill it up, I've got to get rid of things. So let's say, you know, that it wrote things in there and it didn't use up all 10. Let's say it ended up using 7 of them. Well, I've got to get rid of the last 3. So what I can do is I can say, hey, set 3 dot erase. What do I want to erase? I want to erase everything from it, comma, set 3 dot end. So that says erase everything from just past the last one inclusive. So just past the last one is going to be erased all the way up to, but not including set 3 dot end. So it erases everything from just past the last thing written to the very end. So that's one way to do it. That's one way to do it. I'm going to change colors here. Other way to do it. We're running out of room here. Other way to do it. When I do the set union, set union, blah, 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 I would say set union of blah, blah, and I'd say for where to put the results, I would say back underscore inserter parentheses set 3. So that really should be, and then we'd have our functor, and then we'd have the end of the set union. And we don't even remember the iterator. What this says is back underscore inserter. To get a back inserter, you have to pound include iterator is the name of the thing it comes from. Basically, a back inserter is like a wrapper around set 3. And so a back inserter knows that when someone dereferences the back inserter and says, write something here and plus it, What the back inserter does is it says, set 3, why don't you go and do a pushback on that? So it's basically, it's a way to wrap a pushback in code that's going to do dereference result plus plus. That's what back inserter accomplishes, is when you take a back inserter and you dereference and you write something to it and you plus plus it, the back inserter says, hey, underlying container, do a pushback. Done. So that's what's really cool, is that you don't have to presize it. You don't have to erase stuff after it's done. If it was a vector, you could reserve. You could say, hey, let's reserve 10 because I know it'll never be more than 10. But if you don't, set 3 would grow by whatever the underlying container does. Vector would grow by doubling. A dec would grow by adding elements. Okay, so implementing subsets with ranges. So doing this, the initialize, so creating a set would be either O of 1 or O of n log n, depending on whether I want to create an empty one or create one based off of a container. Remember, project 2, part B, sorted binary pairing PQ have a range-based constructor. So we could have our set type could have a range-based constructor, and it would have to not just copy your container full of stuff, it would have to sort it. It would have to do an n log n. Now it says clear here could be O of 1 or O of n. It really depends on whether it's objects, right? If they're objects, we might have to call destructors on all of them. Like if I had a set of strings, I can't just get rid of all the strings in O of 1 time. All n of the strings have to have their destructors run. Is member, so is member, is element, is this thing an element of the set? We could do in log n time with a binary search. So if we were writing our own container and we were basing it on like a vector instead of a linked list, we could do log n searching here. Copying a set would be O of n. It says set union and set intersection would be O of n. Why O of n? Well, because we had to look at every element. Every time I look at an element, I either move one container forward, or I move the other container forward, or I move both of them forward. So n is the combined size of the inputs. So if there's, k in one and j in another, then it's n is equal to k plus j, is the size of the two containers combined. I've got to look at everything. Set intersection, O of n also. Question for you to think about. How would you turn this into set intersection? We're running out of time, so I don't want to go through the changes. Think about it. How would we make this be a set intersection instead of a set union? There's some code that's going to be deleted, some code's going to change. Okay, so and here's some other questions. So if I gave you a sorted range with n elements and a number z, I say, hey, find me pairs, and you could stop with one. You'd stop with one or find them all, but find pairs such that x minus y is equal to z. Or if they aren't equal, find the one that's closest. Or count the ones where x plus y is less than z. And what if it's not sorted? Could you still do these in O of n time? Would you have to sort it first, which would make it n log n time? And the answer to this will also change after the midterm, and we do hash tables. Okay, representing sets and union find. So the idea here is I want to represent disjoint sets, and the example is, let's say we're producing little bases on Mars, and we're connecting them with little ice, like you still got to wear your spacesuit, but there's an electric train, outdoor electric train, still got to wear your spacesuit, but you can get here from here to there faster than walking. And so we start connecting them with these rail lines. Now, as we're doing this, one thing that we do not want to do is we do not want to produce a cycle. Now, Mars names are a little bit hard to read, but like from I'm just gonna try to circle them here. Black. So like if I said, hey, can I make a rail line from that one to that one? it should say, no, they're already connected. You can get there, just ride 2 rail lines instead of 1. You are not allowed to make a rail line connecting those 2 that are already connected. That's a luxury. We can't afford luxuries on Mars yet. Just having the train itself is almost a luxury. We can't afford the luxury of, hey, you can get there in 1 train ride instead of 2. So if someone asks, can you connect those? It would say no. And if I said, well, what about not those? What if I want to connect this one and this one? Yes, you can do that. And moreover, they now have formed a larger superset of the 2 of them. So those 2 disjoint sets have now not just joined together with a rail line, but they've joined into one bigger set. And so as we start forming these, we start having these, we have to keep track of these sets. So I've got the set containing, and here we numbered them instead of names. I've got the set containing 1, 9, 3, 2, 10, 23, 13, 25, etc. And we've also got a bunch of single element sets like 18 and 8 and 4 and 29 are all single size sets. So we want to have a data structure that can represent this and can quickly answer the question, am I allowed to connect these, yes or no? And if I am allowed to connect these, make it happen and make it happen quickly. Okay, so the only 2 operations that make sense are find and union. Find is tell me what set this element belongs to, and therefore if I do a find on X and a find on Y, if the find tells me they are elements of the same set, I would know because they have the same identifier, something like blue and red. Like if I ask about 23 and 10, it would say, they're blue and red sets. So I say, oh, they're different sets. I ask about 23 and 25, it says blue, blue. I say, oh, I can't lay a rail line between those. They're already part of the same set. So we've got to have some way to identify the sets. So I can say, hey, which set do you belong to? Which set do you belong to? If the find says you belong to different sets, then it's safe to do a union to merge those 2 sets into 1. Now that could be simple, like 20 and 21. Hey, they are sets of size 1, we merge them together, done quickly. But if I connect rail line between 23 and 9, now I've got to recolor all of the blue ones to red. Would I have to take them out of one set and put them in another? Could be complicated. Okay, so we've got 2 operations, find and union, and so this data structure that represents this is referred to as a union find, and that's the problem and the data structure to solve the task. So we want to do this as efficiently as possible, and we may have to consider efficiency over the entire lifetime. Say, like on Mars, we get a rail line here, a rail line there, but eventually you'll be able to take a rail line from anywhere to anywhere. You might have to make several stops, but up until the point where everything is connected, we can lay those rail lines. Okay, so we could have these as 2 separate sets. Here, I got to take a pause for just 1 second. I got to tell my wife something. Okay, sorry about that. So I've got these 2 different sets, and I want to know if they're connected. Really, I'm asking, are they in the same set? If I ask about 1 and 6, I would say, okay, they're in different groups, but how long does it take to merge them? You could say, well, it takes the time to merge them would be the size of the smaller set, right? Let's move the least number over, but how do I even know how big the sets are? So that's our cat, it needs to be fed. So union could be as long as O of n, because just to find out, is 6 in group 1? To find out, who are you a member of, I'd have to check every set. Is 6 a member of group 1? I'd have to check, well, is it equal to 1? No. Is it equal to 4? No. 5? No. 8? No. 10? No. Okay, let's move to group 2. 2? No. 6? Yes. Aha. 6 is part of group 2. So I'd have to do linear searches or even binary searches of every set. If they're all disjoint sets or they're longer sets, it could take a while to do those. So union could be as long as O of n, find could be as long as O of n. I might have to check every set, right? If everybody was a disjoint set and I'm asking about 30, I'd have to say, okay, group 1 is size 1, 1 is in there. Group 2 is size 2, 2 is in there. Group 3 is size 3, 3 is in there. So it could take me O of n time to do a find, let alone to do a union. Too long. Remember, eventually everybody's going to be connected. If every find and every union takes O of n, we're looking at n squared for our total cost. Too long. So what if, instead of maintaining these separate sets, what if every set had and knew their representative? Everybody has a unique representative, and the representative is someone in the set. So all we have to do is have a quick way to ask someone, who is your representative? So if I can ask someone very quickly, who's your representative, find is real fast. Union will take longer, but find becomes real fast. So if I can ask someone in O of 1 time, who's your representative? Now, initially, everybody is their own representative. 1, 2, 3, 4, 5, 6, 7, 8. So I ask 1, who's your representative? It says 1. 3, who's your representative? It says 3. Oh, you have different representatives? That was fast. You can be unioned. Well, now I've got to say, everybody who thinks 3 is their representative, change your representative to 1. Okay, join 3 and 8. 3 says my representative is 1. 8 says my representative is 8. You have different representatives. So one of you, I arbitrarily always say the second one changes. The second one changes to be part of the first. Okay, so 8 says my representative is 1 also. I say do a union of 1 and 5. 1 says 1. So when I want to do a union, I do a find first. So I do a find on 1 says 1, find on 5 says 5. They have different representatives. I can join them. So 5 changes its representative to 1. Then I say, can I join 7 and 4? 7 says 7, 4 says 4, yes. So 4 changes its representative, or sorry, yep, I wrote it in the wrong place. So 4, because it got asked about second, 4 changes its representative to be 7. 7 and 2, 7 says 7, 2 says 2. So 2 changes to be 7. And then I say, can I do a union of 2 and 5? Well, 2 says 7, 5 says 1. They have different representatives. So yes, the union can happen, and 5 has to change its representative. But not just 5. Everybody who thinks its representative is 1 has to change. Which means I have to look through everybody, all n of them, to find everybody who says my representative is 1 and change it to 5. And now union is O of n, and that's not good. So union is O of n, but find was fast. Okay, how about we update the smaller one? That would be less work. Well, even then, they could be exactly the same size. They could be both size n over 2, and union is still size n. Also, this representation, this like basically a vector of who is your representative, doesn't even have a size in it anywhere. Okay, so that doesn't work. Smarter union find. Here's the trick. The trick is that you don't have to know your representative. As long as you know someone who knows someone who knows someone who knows the representative, find becomes a little bit slower, union becomes faster, so that's good. So you find becomes slower, seems bad, but union becomes faster. But find was the one that was O of 1. So find becomes a little bit slower, union becomes faster. That's good, right? So now with the I know somebody who knows somebody, again, we start out with all the same representative. And we say, can I join 1 and 6? Yes. 6 changes its representative to 1. Can I join 1 and 8? Yes, they have different representatives. 8 changes to 1. Can I join 1 and 3? Yes, 3 changes its representative to 1. Can I join 5 and 6? Yes, they have different representatives. So I can do it, but I can't just say 6's representative is now 5. I would have to say, hey, 6, your representative is 1, let's go to 1. Oh, 1 says I am really the representative of this group, so 1 changes its representative to 5. And now 6 still thinks 1 and 8 still thinks 1, but they know someone who knows someone who knows someone who knows the representative. So I have to go up to that ultimate representative of the group and change them. So it may take me a little while to get there. Now the problem with this is, what about if I do another union with 6? 6 says 1, 1 says 5, 5 says 5, so I change it again. So I change the ultimate representative of 1 to be 2. Well, but now I change the ultimate representative of 5 to be 2. Now the chain keeps getting longer. So what we could do is, so union is O of 1, find is O of n. It could still be a worst case with a stick. Okay, so the last big idea here is, don't make find read-only. When you do a find, update things. When you do a find, if you find someone that doesn't actually know the ultimate representative, update them so that they do know it. So find gets more complicated, but it'll still be the same big O, but it'll double the work, but it'll still be pretty fast, and it'll speed up future finds. Now the complexity of this one is beyond our class. This is like a 477 complexity. What we're going to tell you is the result. So to get a result on this, you would have to do a lifetime of, hey, everybody starts out disjoint, and eventually there's one big container with that, one big group with everybody in it. Everybody is part of the same group. So the result is, it says this, and this is the total work. The total work from all disjoint groups up to one big supergroup is n times alpha of n. Alpha is known as the inverse Ackermann function. So the inverse Ackermann function, well, what is the Ackermann function? Different Ackermann, not the one at U of M. So the Ackermann function looks like this. 1, 2, 3, 4, 5. It goes like that. Okay? Ackermann of like 5, 5 is great, and it doesn't curve back on itself like that. I actually drew that slightly badly in my haste to draw it very steep. It becomes almost vertical. So that's the Ackermann function. So like A of 5, 5 is greater than the number of particles in the known universe. Therefore, the inverse Ackermann grows very slowly. So that's the, whoops, not infinity, sorry, typo there. So that's the inverse Ackermann function. Alpha is basically the inverse Ackermann for all practical n is less than 5. So therefore, the inverse Ackermann is basically a constant. For all n which are within the bounds of the number of particles of the universe, alpha is 5 or less. So because inverse Ackermann is 5 or less, we're basically, our total life cycle here is O of n times something that's basically 5, which is O of n. Which means, what it means is that the union, when one union occurs, the typical union is inverse Ackermann in length. So the typical union is like 3 or 4. Things need to get corrected to fix it so that I've got an ultimate representative and everybody in the path. Like so 6 says 4 and 4 says 2 and 2 says 1 and 3 also says 1. If I ask 6, who's your representative? It doesn't know. 6 says 4, 4 says 2, 1 says me. But then I update it so that 6 says 1 and 4 says 1. So then in the future, if you ever ask 6 again, who's your representative, it says 1. So basically what we do is we update everybody in the path along that route from that I checked. And the simplest way to do this is with recursion. So I make find a recursive function. It's not tail recursive, but as the recursion unrolls, you set your representative equal to whatever the recursive call returned. And then we're kind of out of time here to do another example. but you can run through the example. You can also look at Professor Darden's piecewise videos. I believe he did the whole example there. So now union is Ackermann of n, inverse Ackermann of n. Find is inverse Ackermann of n. We do n of these, we get n inverse Ackermann of n. Okay, that's it for today. Get some lunch. We'll see you back at Prof's Hours in half an hour.